What's up, guys? It's Mr. Brengle, and today we are going to talk about energy conservation and transformation. So, the first type of energy that we'll talk about is kinetic energy. You watch the astronaut here, he's not moving. Something causes him to move, and he picks up speed. He's moving along there. Well, he has kinetic energy once he's moving. Kinetic energy is simply the energy of motion. So, any object that has mass and is moving has kinetic energy. There's also multiple types of potential energy. So, potential energy in general is just energy that is stored up in something. So, we can talk about gravitational potential energy, which is your energy based on your height or position above some reference level. So, if we lift this AC unit up, it is gaining gravitational potential energy as it goes up, okay? Because if we were to stop it, well, now it's hanging up here, but if you cut this rope, it would fall down, right? So it has stored up energy when it gains height, okay? Another type of potential energy would be the energy that's stored in a spring when you compress it or stretch it. So you can see here when I press start, the person's going to start pulling on the spring. So this spring now has energy stored up in the coils here, because if you were to release it, it would snap back into place, right? And we've kind of already talked about that a little bit with Hooke's law. In Hooke's law, we talked about the force required to stretch the spring and the spring constant, and all that's going to come back into play here. One other type of potential energy that we won't really talk about today is chemical potential energy, which would be like burning of gasoline or when you eat food and your body's breaking down chemical bonds for energy. Okay? So the next thing we need to talk about before we really get going here would be work. So work, a capital W, is equal to the force that's applied to an object times the distance that that force was applied. So in this first lab here, the force that's being applied is a fire extinguisher. So the astronaut's using a fire extinguisher. He's going to apply it over some distance. In our example, we're going to go for 10 meters. And then we're going to turn the fire extinguisher off, and we're going to look at his kinetic energy. The reason for that is because work is also equal to the change in energy of an object. So if this fire extinguisher does work to Wally, the astronaut, over some distance, right? So a force applied over some distance, then he gains energy, okay? And that plays into our conservation of energy. So conservation of energy states that energy cannot be created or destroyed, but it can be transferred. So for Wally to gain kinetic energy, something had to happen to him, right? That fire extinguisher applied a force to him over some distance, and that's why he gained the energy. We can also use this example, the same thing here with the potential energy. I'm putting in these little bricks into the power station, and we are, if you look at the chimney over here, you can see that it's, maybe it's coal or whatever. It's burning coal or doing something to cause this to go up, right? Because this doesn't go up on its own. Something had to lift the AC unit up to that position. Whether it's a person lifting it or a machine lifting it, some sort of energy was put into it to get this to go up, right? So some sort of work was done to this object. Okay, and same thing here with the spring. You stretch the spring. Well, we've applied a force over some distance, and it has gained elastic energy or spring energy. Okay, so let's go back now and let's look at the work to Kinetic Energy Lab. So again, we are going to apply a force of 200 newtons to Wally over 10 meters distance. Okay, so we're going to look at our spreadsheet here, and I've kind of already set this up for us. I've got Wally's mass right here. We are going to change his mass. We're going to keep the force applied the same, and the distance that we apply that force is also going to be the same the whole time. So this first part here, we need to calculate the work that was done to Wally. Well, that's simply just his force times the distance that force was applied to him. So the answer here should be 2,000 newtons in every case. His mass doesn't matter here. This is simply talking about the force that the fire extinguisher applied to Wally for the distance that it was applied for. Okay. Now, what we're going to do here is we're going to look at, as Wally is released here, I'm going to do this one more time. So I'm going to let the fire extinguisher go for 10 meters, and then he's going to fly across at a constant speed because he's in outer space. And then this distance right here, 10 meters, it's going to time how long it takes for Wally to get from this side to this side. And then we can use that time and this distance here to calculate his speed at this point. And then we'll use his speed to help us calculate his kinetic energy. Okay, and we're going to look at his kinetic energy compared to the work that was done to him. All right, so let's start this out at 35 kilograms, 200 newtons of force. We'll reset this. His backpack is at 0, so when his backpack gets to 10, I'm going to stop it. Okay, I'm going to try that one more time. There, that's a little bit better. And we'll let him go here. And then you can see the time that it took for him to go through the photo gate was 0.931 seconds, because that is in milliseconds. So I have his photo gate time, and I know the distance that he covered was 10 meters. It took him 0.931 seconds. So to calculate his speed, all I have to do is his distance divided by the time it took him to cover that distance. I now know that he was moving 10.74 meters per second. Then we can calculate his kinetic energy, and that is equal to 1/2 times his mass times his velocity squared. So I'm going to put in 0.5 times Wally's mass times, in parentheses, his velocity squared. So I'm going to click on the velocity. I'm going to square this here. Okay. So you can see that his kinetic energy that he gained during that time was 2019 joules. Well, that's pretty close to the work done by the fire extinguisher. Now, these numbers are solid. We know that this is what's supposed to be the answer. This number, the kinetic energy, is going to be dictated by how accurate I am at stopping him at exactly 10 meters. Okay, so it's not going to be exactly 2,000. There's going to be some user error in there, but that's pretty close. So let's now change his mass to 55 kilograms. And let's do it again. Perfect. So we'll let this go. So we kept the force the same. We kept the distance that the force was applied the same. We did change his mass, however, and you'll notice that the photo gate time increased here. It's now 1.173 seconds. Okay. So what I'm going to do here is I'm going to go ahead and drag these calculations down. So you can see that his speed decreased when we increased his mass from 35 to 55. And you can see that his kinetic energy that was gained here is 1,999. So that was pretty accurate. So again, the work that's done to Wally each time is 2,000 joules. So the kinetic energy that he gains should also be around 2,000 joules. Okay, which is again based on how accurate I am with stopping the force that's applied to him exactly at 10 meters. Okay, so let's go ahead and do the last one here. We'll bump his mass up to 75. Okay, that's not bad. It's a little bit off, but that'll be okay. And you can see again, he's moving slower here. And the time that it takes him is 1.359. So again, the time it took him increased because his mass is increased. So greater mass, harder to accelerate that object, won't be moving as fast when we stop applying that force. So his speed is decreased, and you can see again, we're right around that 2,000 joules mark of energy that was gained by Wally. So you can see that that works out pretty well there. So the kinetic energy of the object is based on the object's mass and speed. Okay, so when we increased the mass and applied the same force for the same distance, Wally's speed decreased, okay, as the mass increased, and therefore his kinetic energy would stay about the same because you're increasing mass, but you're decreasing the speed, okay? Let's go ahead and look at our next little lab here, which is potential energy. So what we're going to do is we are going to choose some different masses. There's some different things here. And we're going to raise them all up to 2 meters. Okay, so I've already put this in here. We've got the masses put here. We've got the gravitational field, or the acceleration due to gravity, set at normal Earth conditions, and we're going to raise each of these objects 2 meters into the air. We're going to look at how much gravitational potential energy was gained by each of those objects by looking at this equation here. We're going to multiply the object's mass times the acceleration due to gravity times the height that the object was raised to. So the masses are preset, the height's preset, okay, and our field strength here is preset. So we can actually go ahead and calculate all of these. What we're interested in is in the lab, it's going to tell us up here how much energy was used to move the object up to 2 meters. And that is going to be the work that was done to the object, right? So that energy that was used right there should be equal to the work that was done to the object, which should be equal to the potential energy, the gravitational potential energy that was gained by the objects. Okay, so we want these two numbers to basically be the same. Okay, so it's very similar to what we just did. So let's start with the AC unit. We'll put one of these power bricks in, and you can see the bottom is down here, so I'm going to lift this thing up to 2 meters. Okay, it's maybe a little bit too high, but that's okay. You can see the energy used here was 2.44 kilojoules. So I'm gonna go ahead and multiply that by 1,000. So 2,440 joules. Okay, so we're just multiplying this by 1,000, moving the decimal place over 3 times. Okay, so that's how many joules it would be to raise that object that high. Let's go ahead and do this calculation. Equals the mass of the object times the gravitational field strength times the height of the object. And you could see that that's right around 2,400 again. I think I let that one go a little bit too high. So let's go ahead and try the next one here. So we'll switch this to the bathtub, which is the next one. We'll put in a power bar. We'll raise it up. Okay, so this time 3,700 joules to raise it, which is the energy used up here. So 3,700 joules. I want you to notice that the mass of the AC unit was lower than the bathtub, and it did take less energy to raise the AC unit than it did the bathtub. Okay, so let's go ahead and do this calculation here. Mass times gravitational field strength times the height, and we get 3,704. So that one was a lot better. I think I stopped it where it was supposed to be. So that one matches up nicely. Now let's reset this and change this to, I don't even know what these are. I think they're maybe like pallets. So we'll raise these up. We'll stop it right there. So again, we increase the mass again, so it's 236 kilograms now, and it took 4,540 joules to raise the object. This time, again, a greater mass, greater energy used. We'll go ahead and do this calculation again. Mass times field strength times height, and it comes out to 4,600, which is pretty close to what we got. Again, this is based on user error, so these aren't going to be perfect. Let's go ahead and reset it for the bricks. And we'll let this raise up to 2 meters here. You can see it's moving pretty slow. So we kind of got to wait. But again, increase the mass. This time it's 6,090 joules to raise it up. And then our calculation here shows that the gravitational potential energy gained was 6,100. So again, very close there based on user error. As long as it's in the right vicinity, we know that we're doing something right here. And then our last one would be the safe here, the heaviest object. And we'll raise that up. and it didn't even make it to 2 meters here. Okay, so it actually just made it to 1.8 meters. So we can make an adjustment on that. But it did go to 8,360 joules used. 8,360 joules used. I'm going to change the height to 1.8 meters because it did look like it got to about 1.8. And then we will do this calculation here, and it comes out to be 8,500. Okay, so not too bad. So you could see that the energy that was used, which again, remember, this is the same thing as the work that was done to the object, should be equal to the gravitational potential energy that was gained by the object. The only reason these aren't exactly the same is because it depends on me stopping this object at exactly 2 meters. Okay, if it goes to exactly 2 meters, then it should match up. Okay, obviously these are estimations here. So point there is the work done to the object is equal to the gravitational potential energy gained by the object as it increases its height. Okay, let's go ahead and move over to our spring energy now. So the main thing I want to show you here is just looking at this. We're going to spend very little time on this, but when I click start here, you see the person pulls the spring back and it stretches the spring. You can see that there's stress on the spring here, and if this were to let go, if we were to let go right here, that spring would snap back, right? So there's all this energy that gets stored up in here. We applied a force to this object and stretched it some distance, so work was done to the spring, which means that there has to be potential energy that was gained by the spring. In this case, it's stored in the coils. When you let it go, it's going to snap back into place, right? Okay, so again, just to show that pulled over some distance, you can see the force meter in the top right corner that's increasing as the distance increases here. All right, now what I want to talk about is that, you know, it doesn't have to always be work done to an object that and then it gains some type of energy. We can transfer energy too. So let's look at this lab here. What we're going to do is we've got a little hockey player here, and we're going to compress this spring, you know, some distance, and then we're going to fire the hockey player on frictionless ice. And now what's happened here is when we compress that spring, so let's go back to that and let's look here. We compress the spring some distance, right? We've done work here. And so this spring has gained some energy, and by an extension, Trevor, the hockey player, has gained energy. Elastic energy is stored in this spring, and it's about to shoot him off. So once he gets shot off, and he's no longer in contact with the spring, he no longer has elastic energy. But he's moving, so he must have kinetic energy. So what happened here is all of the elastic energy was transferred into kinetic energy for Trevor. Okay? So what we're going to look at is we're going to go back to our spreadsheet here, and we're going to look at 3 different spring constants. So you guys will remember that spring constant is essentially how stiff the spring is. It's how much force is stored up in each meter of the spring. So we're going to increase our spring constant. We're going to make that spring more and more stiff. We're going to compress the spring 1 meter each time. And then we are going to see how much force, what's the restoration force. So remember, the force that we apply to the spring to compress it would be equal to the force that's pushing back on us, that's trying to restore that spring to its initial position or its equilibrium position. So we'll calculate the force there, which by using Hooke's law, which we've already done in previous labs. Force, the restoring force, is equal to the spring constant times the stretch or compression of the spring. So we can go ahead and calculate that. And then we're going to use that to calculate elastic energy, okay, or spring energy. And that's equal to 1/2 times the spring constant times the stretch or compression of the spring squared, okay? So let's go ahead and do that. So we're going to do force is equal to spring constant times the stretch or compression of the spring, okay? So these should be very simple calculations here. So the force that's used, 500 newtons, 1,000 newtons, 1,500 newtons. Now to calculate the elastic energy that's stored in the spring, we're going to do 1/2, so 0.5, times the spring constant, times the stretch or compression, in this case, squared. Okay, so you can see that as the spring constant is increasing, we are also increasing the elastic energy that is stored in the spring. And that should make sense. If that spring is really stiff, it really is fighting hard to push back to its original position, right? It's a lot harder to push this or to compress this spring or stretch it than it is the 500 Newton per meter spring constant spring, okay? So ultimately what we're going to do is we're going to compare the elastic energy that was stored in the spring to Trevor's kinetic energy once he's shot off. So the first thing that we have to do is calculate Trevor's speed, okay? So it's very similar to what we did in the Kinetic Energy Lab on tab 1 here. But we need to calculate his speed. It's actually given us a known distance here between these blue lines, 18 meters, and then we're going to time him from blue to blue. And again, this is going to be user error, so I'm going to have to start and stop the clock at exactly the right time to get exactly the right numbers. We know that that's not going to happen, so what we're looking for is that by the end of this, when we get Trevor's speed and convert it into kinetic energy, or use it to calculate kinetic energy, we want these numbers to be pretty close to the elastic energy that was stored in the spring, okay? So I kind of already had some mock data here, but let's go ahead and look at the time it takes him when we do 500 newtons per meter spring constant, a mass of 50 kilograms. I'm going to pull him back 1 meter, so his back is at 1 meter. When his back reaches the blue line here, I'm going to start the clock, and then when his back reaches the other blue line, I will stop the clock, okay? So he's going to move across this known distance at a constant velocity, and I've stopped it at 5.8 seconds, so we'll go ahead and put that in there, 5.8 seconds. And then to calculate Trevor's speed, remember, speed is distance divided by time. We know the distance, we know the time. We can do distance divided by time, hit enter, and that gives us his speed, okay? Let's go ahead and reset Trevor at 1,000 Newton per meter spring constant. So we'll pull him back the same distance. We'll leave his mass the same. The only thing we're changing is the spring constant. You can see he's moving a little faster now. Okay. All right, so 4.04 seconds. This isn't going to be perfect. We'll go ahead and look at his speed. So what we should be thinking here is that since the spring constant increased, that means that the force that was used to compress the spring was increased. Therefore, the elastic energy that was stored in the spring increased. So he should be shooting off at a higher velocity, which indeed he is. And then we'll go ahead and we'll do this last one here where we change the spring constant to 1,500. We'll pull Trevor back, compress him 1 meter. Once again, we'll fire him. Okay, 3.28 seconds. This is not going to be perfect by any means. We'll go ahead and look at his speed there. Should have increased again. And indeed it did. So now what I've done is I've made another table down here with Trevor's mass and speed, because those are the things that affect his kinetic energy. So we're going to go ahead and calculate that just like we did in the previous example. This is going to be equal to 1/2 times the object's mass times its velocity squared. Okay, so 240. Not too bad. The elastic energy in the spring was 250. And we'll look at the other ones here. So 496 compared to 500. So I did a good job on that second one. And then 252 compared to, or I'm sorry, 752 compared to 750. So I did a pretty good job on that last one there too. So what this is showing you is that all that elastic energy that was stored in the spring, assuming a frictionless surface, was transferred completely into kinetic energy. Obviously this first one wasn't great, but these were a lot better. Just showing you that transformation from elastic energy to kinetic energy. And of course you could transfer gravitational potential energy to kinetic. What would be an example for that? Well, how about when anytime you drop an object, right? It has some height, you drop it, it loses height, but it's gaining speed. So as the object loses its height, it's then gaining speed, and therefore it's losing gravitational potential energy because it's being transferred into kinetic energy. So we could look at that here with this lab. which is just Isaac Newton dropping a ball here. Okay, so as he drops this ball, you can see it's speeding up, speeding up, speeding up. Well, it's gaining kinetic energy as that happens, right? And it's losing gravitational potential energy because it's being transferred into that kinetic energy. Okay, so now in real life, energy transformation is not 100% efficient, right? Like, it's not realistic for us to have a completely frictionless surface like this, right? So there is energy loss, and I want to show you that with this. If there was no energy loss in real life, what would happen is when he drops this ball, it would bounce and it's going to come up to the exact same height. But you guys can see that when it's dropped and it bounces back up, it's never going to reach the same height, right? And you guys have probably done this before with bouncy balls. It never reaches the same height. Well, why is that? Well, most people say that energy is lost, but that's not really the right term. It's more that energy was transferred out of the system that we are talking about. So in this case, what happens is the ball hits the ground and you hear it, right? You hear a thud. Well, what that thud is thermal energy, okay, that's being released. So some of the kinetic energy from the ball, when the ball hits the ground, it's then transferred into elastic energy as the ball compresses. And then the elastic energy is then transferred back into kinetic and gravitational potential energy as it moves back up. Well, some of that energy is transferred into heat energy or thermal energy that is more or less, in quotations, lost from the system. Okay, but really it's just transferred from one type to another. Okay, we'll talk more about the system and what that means later. But the point is that in real life, you're not going to see 100% efficiency in transfer of energy. Most of the time, friction and thermal energy that's created by friction is where you're going to see that quote-unquote loss in energy. Okay, so there's a tutorial on energy conservation and transformation. We will work a lot more with this in the coming days.